Alright, so this section's on the photoelectric effect. So what I'm going to do is just walk you through this diagram here. Whoops, I'm going to walk you through this diagram. Pen, does this thing work? No, I've got to do it over here. Okay, so, alright. So let me just, where we're going to be going with this is I'm going to actually turn things on its head a little bit. I'll just warn you here. But let's look at this experiment because it's a pretty important one. So I'll just walk you through this. There's what's called a photocell. So it's basically just a shiny plate. And what you do is you shine light on it. Okay, so far so good. Now the interesting thing is, if you shine the right light on this photocell here, it will actually release electrons. Now, in a way, that's not so surprising, right? If you pump energy into something, you would expect, perhaps, given that light interacts with electrons, if you pump enough energy in, you should be able to push some of them off the photocell. That kind of makes sense to me. So, when you do so, they end up over here on this collector, and then what can happen is, can you see here that you'd get, this would be kind of negative, and then of course this thing's lost electrons here, so this would be positive there, right? And so electrons would then flow if there's a wire connected around here. Now let's go, okay, let's say they're just flowing through in this direction. In fact, they don't, they end up flowing this way. So flowing this way around here, long story why, doesn't matter, flowing around, and then they end up back where they started. So basically, we've got a current being produced here. So, okay, so what? Well, we can actually measure the current. The current is measured in a thing called amps. You don't really have to know that, but there's our measurement device measuring these electrons moving around in this system here. So okay, now what this other bit here is where's my thing? Okay, this bit here it's basically a battery arrangement, and this is the negative end of the battery here. This is the positive end, and if I turn the battery on, if this is positive here, this means this is positive here, and this can kind of hold the electrons back here so they don't move. So you can play around with how big the voltage is here, and at some stage you can actually stop them from being ejected here. Now, you don't have to know any of that per se, but I'm just trying to show you that that this is the experimental setup that was used, and the reason it was of interest is because you could then figure out the relationship between the amount of light incident on this photocell here and whether electrons were ejected, and also you could figure out how energetic those electrons were. Okay, so people do these experiments. Now, before I show you what they actually have found, I just want to relate this back to everyday life a little bit. So if I go to the next slide, I know this looks like a pretty weird kind of simple slide here. Now this thing's working for some reason, who knows why. In this slide here, what I've done is I've tried to illustrate where I've got floating buoys that's B-U-O-Y-S on the water, and as a wave passes through, let's say those buoys, obviously they're tethered down here to the bottom of the ocean here, and as those waves move through here, those buoys will move up and down. Now, let's imagine two situations, and what we're really interested in this time is the amplitude of the wave, like how big the wave is, how intense it is in terms of the amount of energy it's punching through per unit time. Now, if you didn't quite understand all those terms, it doesn't matter. The idea is very simple, right? If you're just generating little ripples like this, so they're quite small, the buoys are just going to bob up and down a little bit and it's not a big deal. However, if you push through waves with great big crests like this, they're going to have more energy in them. And if they're energetic enough, they'll be energetic enough to actually push these boys away and break this tether here, right? Now this is, in a way, what's happening with the photoelectric effect, right? You're shining light on a plate that's, instead of buoys now, we've got electrons, and that light is pushing those electrons away. And the interesting point here, and the analogy holds perfectly, is that what's really of great importance is the amplitude of the wave. I mean, it doesn't matter how frequent the wave is going through here, right? If it's a little ripple, doesn't matter how frequent it is, nothing's going to happen to those buoys. And it's the same, you would think, with electrons, right? What's really important is the amplitude of the wave, which you can measure as wave intensity. Now, here's the kicker. So in the photoelectric effect, what one finds is that you can shine the most intense light you possibly can onto that plate, which means it's got a huge amplitude, and yet no electrons are ejected. Now, when you go back and look at that, that makes absolutely no sense, right? Because if the amplitude's big enough, surely it's got to push these electrons off. So look at this, and this is shown time after time in experiments. So here we've got, hello, I've lost my thing again. Here we've got a case where at this particular wavelength, 700 nanometers, no electrons are ejected. It doesn't matter how big the wave is, you can't push the electrons off. Now, that's nuts. That makes absolutely no sense whatsoever. And yet, if you get to the right frequency, right, in this, well, or wavelength, it's the same thing, right, then they do push off. What? Okay, so this is the issue that actually Albert Einstein grappled with, and the only way that he could figure out that it made any sense is if you said, well, okay, light doesn't actually behave as a wave, at least not in this instance. It's not behaving like these guys. It's behaving like light is actually in little packets, right? And those packets are called quanta, because it's a discrete unit. And he then went on with some very fancy mathematics to figure out that if you do all of this and you assume that these that light actually does behave in these little packets, they're now called photons, right? You can then actually derive an equation to calculate how much energy is in a particular photon. So there's the formula there, which you've already seen. I kind of glossed over this a little bit, actually. This energy value that you calculate here, E equals h nu equals hc on lambda, this energy value here is not just for the entirety of the light that is shining on it. It's actually calculating the energy in one little packet, this thing we call a photon. Now, can I just suggest, like, that the equation itself is ridiculously simple. Please be a little humble about this, because it looks obviously simple, but if you actually follow all the reasoning and the thinking, it is actually a beast to try to understand. And there's the original derivation of this formula, etc., using Planck's constant. Okay, so in summary, let me just skip through here for a sec. Okay, so in summary, we're now starting to get some pretty kind of odd ideas. So one is that electrons seem to be sitting in these quantized energy levels, that light seems to have all this almost this dual behavior associated with it. In one instance, you do the experiments like a double slit experiment and the stuff behaves like a wave. And then in other experiments, like the photoelectric effect, the thing behaves like particles. Now, I will say this. When in our world, the everyday world that we live in, our model of the world is basically that things are either particles or waves. There's nothing in between. Now, there's nothing written anywhere that says that the universe always has to behave the way we observe it in our world. So just keep that mindset when you're looking at some of this stuff, right? If you ask the question, is light a wave or a particle? My response would be, well, actually, I think you're actually asking the wrong question because you're presupposing that things can only be waves or particles, right? So depending on the experiment, as you can see, light can behave as a wave or a particle. What is it? Well, it's this thing that's kind of like a mixture between them. Now, it's hard for us to conceptualize that by analogy. We actually really start clinging to experiments, right? So we basically end up saying things like, okay, in this instance it's a wave, in this instance it's a particle. What is it in reality? It's this kind of thing that's very hard for us to conceptualize, right? Because there's no everyday analogy for it. Okay, I'm going to leave it there, and then I can move on to the next section.